In the last class, we have learned how to model a plate using 3D solid element. 3D solid element. So there we have learned how to model a composite plate using C3D8R element, and then again we have learned how to model using C3D20R element. So there we have learned how to model it and then how to get the converge result, and then we have learned how to get the frequency. We have learned how to get the frequency and then how to get the converge result, and then we also have learned how to save the data. So there we have learned that eigenvector is a one special vector when it operates on a matrix, when it operates on a square matrix, it is to give the same vector with some multiplication constant. Okay. Now we can write eigenvector in this equation. Okay, so basically eigenvector is a vector which does not change its direction. Okay, when we have a vector like this and when it operates on a matrix, it used to have the same vector with some constants. Basically, this constant may enhance the vector magnitude of the vector, or it may contract the magnitude of the vector, but direction of the vector will remain same. So there we also have learned how to solve it. So in that case, what we have learned that we can solve this problem. We can solve this problem by taking x as a common. And here, if we take x, when we take x as a common vector, okay, and then we can write a minus lambda into I. So I is here identity matrix. So if you want to solve it, in that case, we have to take determinant of it as a 0, since a cannot be 0. Since a cannot be 0, a not equal to 0, so this part should be 0. And if you take the determinant of it, we can find the lambda. Okay. Again, we have learned that eigen solution is a two-step process. In the first step, we used to obtain the eigenvalue. Once we obtain the eigenvalue, what we used to do, we used to put the eigenvalue here again, and we used to find what is the value of x so that this value comes 0. Okay. So now we used to find the value of eigenvector. So this is the way we used to find. Now problem here was that we used to deal with two matrices instead of only one matrix. We used to deal with two matrices, that is your mass matrix and a stiffness matrix. Okay, so here also what we used to do, we used to find a common eigenvector. When it operate on a mass matrix and a stiffness matrix, it used to give the same eigenvector along with some multiplication constant. Okay. So if we do it, so here basically you can see we used to find phi eigenvector phi such a way that when it operate on mass matrix and stiffness matrix, okay, it used to come the same vector. If you can write in another way that minus m omega square, okay, or other way you can write that k, you can write k is a matrix. If you operate on a vector, it is to give the same vector when it operate on a mass matrix along with your some multiplication factor. So we can write in this way. Okay. So though we initially learn what is eigenvector with a single matrix, the same principle is applicable here also. Here we used to find the eigenvector when it operate on mass matrix and a stiffness matrix. It is to have the same eigenvector with some multiplication constant. Okay, so since this phi cannot be 0, so we used to make this part and we used to take determinant as 0 and we used to find omega. Once we find omega, then again, or once we find the omega square or lambda or eigenvalue, once we find the eigenvalue, we used to put that value again here and we used to find what is the value of phi. Okay, this is the way we used to solve. So here, what we'll try to do, we'll try to model this. Here we try to model this composite plate. Okay, here we'll try to model this 3D composite plate in a layerwise manner. So here we'll try to model this composite plate in a layerwise manner. Let us go to ABAQUS and we'll see how we can do that. In this This part we have already learned. Now what we're going to do, again we'll create a model. We'll create a new model here. Here in the model 1, we can create model 2. Okay. Now in the model 2, we'll go here in the model 2. Now we'll create a part. Our part will be solid and maximum dimension I'll keep it 1. And now what are you going to do? I will choose two opposite corner. One corner is your minus 200 e to the power minus 3, comma minus 150 to minus 3. Okay, and opposite corner is 200 e to the power minus 3, 150 and 150 to the power minus 3. This is the way we can create the geometry. And now we'll give the thickness. Thickness is our 10 mm, 10 e to the power minus 3. So 10 mm is our thickness. This is the geometry of the plate. Now what we are going to do? We are going to define the metal property. So here what we are going to do? We are going to define the metal property. So metal property will define as metal 1 and density we have learned that is 1960 kg per meter cube. And in the mechanical property we will go elastic, and then in the isotropic we will go for engineering constant. And we'll give the property as 35 GPa, 35 E9, 30 GPa, E2 30 GPa, 30 E9. That E3 will consider as E20 GPa, 20 E9, and Poisson ratio will consider 0.25 and 0.25, 0.25. G12 will consider 7 GPa, 7 E9. Now we'll consider 5E9, and then again this is 5E9. Okay, this is the property we'll consider now. Okay. Now what we are going to do, we are going to assign the property in a layerwise manner. This geometry. Here we are going to assign the property in a layerwise manner. This geometry. So we'll choose this option. We are not going to choose these options or these options. We'll go for this option, composite. Create composite layer. So here we'll create composite layer. Now here I'll count as the initial ply count as a 4 layer. So since it's demonstration, so I'll choose only 4 layer and I'll choose as a solid. Now here what we have to do, we have to define the ply name 1, 2, 3, 4 in the region. We have to define the region. So here we can select this one and again click here. You can select this body. Okay. If you want to define the property in all the region, if you define that ply 1, ply 2, ply 3, ply 4, okay, and the region is the same. Okay, if you want to define ply 1, ply 2, ply 3, ply 4, and the region is the same, then here you can click, okay, and you can select this body. Here you can see you can define at once. Okay, now here we have the metal property, one metal property. So what I can do, I can double click it here, and okay, click is not working, so I can right click it here and you can select edit options. Now for edit options you can select material 1. Now here you can see we have selected material 1 for all the ply. Okay, so now if you want to apply different material, whatever you do, you have to initially create the material library. The material, okay, initially you have to create in the material library as a material 1, material 2, material 3, material 4, like that. Okay, if you want to define different material property in different layer, then you have to create the material library as a material 1, material 2, material 3, material 4, and there you have to define their property. So here I want to apply the material property for all the layer so that I can check whether our frequency is coming same or not. Whether we can consider 10 mm as a single solid element. Okay, whether you can consider 10 mm thickness as a single solid element, or we can consider 2.5 mm of 4 layer, and whether we are getting the same frequency or not. So here what we are going to do, here we are going to we are going to check whether 4 layer of 2.5 mm and 1 layer of 10 mm we are giving the same result or not. Since already we have learned how to model a composite using 3D solid, there we have only 1 layer and we have defined the properties. So here what we are going to learn, here we are going to define the same metal properties in 4 layer, and we want to see whether we are getting the same frequency or not. Okay, so here we have defined the ply name, define the region, we also have defined the metal property. Now here it is asking the element thickness. So what we can do, we can write 2.5 mm, so it minus 3, 2.5 to the power minus 3. Here also 2.5 to the power minus 3, and here also 2.5 to the power minus 3, and here also 2.5 to the power minus 3. So now you can see we have total 10 mm thickness. Now here it is asking the CSYS for each layer. For each layer, CSYS basically datum point they are asking for each layer. So here we can select datum for all. Okay, so here you can see by default it is selecting like this. Okay, it's fine. Now here it is asking angle of orientation. Okay, so here it will be 0, 0, 0, 0. Okay. Now here it is asking integration point. We can give 3-point integration. Okay, so or 1-point integration also we can do. But here I have chosen 3-point integration. Okay, now one more thing we have to do, we have to define the layout orientation. Here we have to define your coordinate systems. Here we have to define your coordinate system. So how to do that? We have to create datum line here. We have to create datum line here. So here we can choose datum 1 as a rectangular. So here we choose rectangular. Now you have to be you have to be very careful here. Here it is asking that select the origin. So I am selecting origin at 0, 0, 0. Now here it is asking select a point to the x-axis. So here you can write 1, 0, 0 in x-axis. Now it is asking select a point in the xy plane. So we can write 1, 1 and 0. So it is in xy plane. Now in this way we can define a datum. Okay. Now what I am going to do, I am going to select it, and I am going to select the datum 1, and then we just click OK. Now here we can click OK. Now here you can see now our property has defined. Since the color has changed, so you can since the color has changed, so it is basically indicating our property has been defined. Okay. Now what we are going to do, we are going to go for assembly. Here we'll create your dependent instances. Next we'll go for step. The step we used to define what type of analysis we want to perform. Here we'll select linear perturbation, and then we'll select frequency, and then here we'll choose lamp pose, and here we select first 5 frequency, and here our minimum frequency of interest I am putting as a 1 to avoid the rigid body motion. Since we are not providing any boundary conditions, so there will be 6 rigid body modes. So I want to avoid that. So I am putting our minimum frequency of interest as a 1. Okay. Now what we will do, we have to go for meshing, and then we have to submit the job. So here we'll go for the meshing. So meshing here we have to do in the part. Just select here, and then we just select these options to make a wireframe. You just select these options to make the wireframe. Now here I will select the edges 1, 2, 3, and 4. I'll define 40 element on the I define 80 element on the longer edge, and here I will define 60 element on the shorter edge, and along the thickness I'll define 4 element. Along the thickness I'll define 4 element. Here I'll define 4 element. So I'm creating 4 node here, or I am defining seed value as a 4 to create 4 node there. Now what I am going to do, here I am going to select as a, here I'm going to define the meshing. Here I'm going to define the meshing. So I have defined the meshing here. So here I can select this option, and I can see the meshing here. Now what I can do, I can go for Run. Now here I will create. Here I will create your job 3, that is your your plate layer wise. Layer wise. Now our job is plate layer wise. Now I am going to submit it. So I complete this part and submit it. Okay, now I will check the frequencies and I will see whether we are getting the same frequency or not. Again, we will try to change our angle and we'll see whether frequency is changing or not. That also we can do. So here you can see it is showing file processor has completed, so there is no error. If you want to check the error, here you can click, and from this option you can find error warning, all the things you can find. Okay, the job is still running. We'll wait for some time. Now job has completed. Now we'll go to the result. On the form shape, here you can see first frequency using your solid element is coming 159 solid element, and we're defining the property as layer wise. So here first frequency is going 159.43. Next we have 255.90. Okay. Next we have 418.69. Next we have 441.10, and next we have 534.20. Okay, so here also you can see the error what is coming is less than 1%. Okay, now what we can do, we can go for meshing and we can choose higher order element. So here you can see initially we have chosen C3D8R element. Now we are going to choose quadratic element and we'll run the program and we'll see how much result we are getting using your higher order element. But again, it will take a little bit more time. You have to wait. Okay, so in between, you just do one thing, you note down your result with your C3D8R element, C3D8R element with 4 layer. Okay, now we'll get C3D20R element with 4 layer. Okay, so we'll see how much result is changing. Okay, so once we get this result, next job will be to check our orientation from theta 0 degree to 90 degree. Okay, and we need to check whether our result is changing or not. Next, our job is to change the angle of light, and we need to see whether our result is changing or not, whether that analysis what we are doing here is correct or not. So what we did, we initially model using 3D solid element, and then we define the property, and we define the property as a solid, and we define the property as a layer wise, and we have selected 4 layer. In the 4 layer we have defined same metal property and with the angle of 0 degree, and we got some result. Okay, and now we did the same analysis using C3D20R element. We'll get some result. Next we'll change the theta and we'll see how our result is varying. Okay, so this part we'll do, and next we'll see how we can save our more saves, how we can copy it and make a report on it. It is taking a long time, so I have to wait. So here you can see, since our degree of freedom increases, okay, initially we use 8 node element, now we have used 20 node element. So each element will have 20 node and corresponding degree of freedom. So here you can see our degree of freedom increases in large extent. So our computational time also will be large. Here also you can see. So here you have to take some judgment. How many number of element you should have and what type of element you should have. So that judgment you have to take. Otherwise, it will take long time to get your solution. If you increase, if you discretize the element in a more finer way, it will take long time to get the solution. Okay, so here you could take some judgment so that you can get some converged results. So first of all, what we are going to do, we are going to see what is the result is coming using 4-layer. So now we are getting result as 163.90. Next result is your 269.68. Next we have 428.01. Next we have 455.54. Now we have 550.43. So here you also can see the result has changed. Okay, now result is little bit higher inside. So we can judge it once we model the same thing using cell element. Okay. If you observe that your cell element and C3D20 element are giving close result, then it will be better if you use either cell element or 3D solid element. Okay. So again, again, it's up to you which type of element you want to use. Okay. If you want to see at how the stress, strain, and other quantity is varying along the thickness, then you should use 3D solid element. If you want to see only the mode shapes and the frequency, in that case you can use cell element. Again, you have to take precaution because cell element used to give good result if your thickness is less. If your plate having higher thickness, in that case you should use solid element. Cell element in such cases may not give accurate result. So here we have learned that how we can model a composite plate using a layer-wise manner. Okay, how we can model a composite in a layer-wise manner. So here we have modeled the composite plate using 4-layer and all the degree of angle here, all the rotation angle we make it is 0. Now what we are going to do, we are going to change this to 90 degree. Here also I am going to change this to 90 degree. Now here we will see that what are the result are coming, how much frequency is changing. If you observe that frequency is changing, that means the property you have defined here is acting correctly. Okay, the model also is working fine. So here again we'll submit, but here we'll see that here we'll see. Okay, we'll submit it again. And we'll see how much result is coming with 090, 090. Since we have changed the angle, the result should change. We don't know how much it will change. But if you observe that there is some changes, that means our angle initially the angle we have assumed 0, 0, 0, that is working fine. Let us wait for the result. Now result Now job status is completed. The job status is completed. Let us go to the results. So result here you can see it is now 163.80. Initially it was 163.90. And next mode we'll see. Next mode we'll see it is coming 260.32. Earlier it was 269 and 421. Earlier it was 428. Next we have 473 now. Earlier it was 455. Now it is 563. Earlier it was 550. So now here you can see once we change the angle, from 000 to 090, our frequency is changing 09090. Okay, 09090. So you can see that our result is changing. So here you can see that means the property we defined through this layer wise manner is acting correctly. One more thing you just see, once we use a single layer, okay, in that case once you use a single layer solid element, in that case our frequency was coming to nearly 150. Okay, and once we compare the result for the of the composite model using one layer 3D solid element and whole layer of 3D solid element, we can see both results are very close. Okay, so here you can say that if you use as a layer wise composite, then also you can have a acceptable result, and result is error in different model. The result which is we are getting in different model, error between that result is less than 1%. Okay, so you can choose any model, either solid model, solid single layer model, solid multi-layer model. You can use 3D8R element, or you can use 3D20R element. In all the cases, we are getting our acceptable result. Okay, now you have to take the judgment for your model and you have to proceed further. Next, what we're going to do, we're going to model. Here, you can apply the method property in other way also. To this one, create, and here if you are creating the geometry using 3D solid. Okay, so here you can see we have initially assume element type solid. Okay, instead of having solid, you can use continuum cell. Okay, you can use continuum cells, and you can click on continue, and the same way you can define the property. But here you have to check the result. Here you have to check the result whether the result is coming correct or not. Okay, here also you have to define all the parameter here, and here also you have to define that layer orientation. Okay, here also you have to do this part, and you can check your result. And there is also other way, that is your by going through this one. Here you can, once you define the material property, now go to here, select cell, then here instead of homogeneous you select composite, and here also you can define the material properties. Here you can define material property as a material 1, here material 1 like this. If you have material 2, you can choose material 2. Here you can define the thickness, orientation angle, integration point, line name, that thing you can select. Okay, and that thing you can define here, and then you can again you can define it through this part. Okay, like this one. Okay, so here this way you also can define. So you have basically 3 options to define the property as a layer wise. But my suggestion is that once you are modeling it as a 3D solid, in that case you choose this option and then go for solid, and you define the layer here. Okay, if you are modeling part as a 3D solid, and then you have to check your result using that your continuum cell element. Okay, if you model it using continuum cell element along with the part as a 3D solid, part in 3D solid, and here material property layer wise, but in a continuum cell element, that case you have to verify your result. If you see that your result is coming satisfactory, in that case you can use. Okay, so this option you can use. That is secondary option, and this option also from here you select composite cell and then composite. You define the property in layerwise. So in this last two case, what we have discussed, you can choose this option, but you have to verify your result. If you see the result is coming as per your expectation, then you can use this option.